We have an example problem here. A 10 microfarad capacitor is charged to 15 volts and is then connected across a 5 millihenry inductor. What is the charge on the capacitor when the current in the circuit is 0.55 amps? All right, so we're bringing in a capacitor that has charge already stored on it. Okay, sorry, my computer's at a very slow operating stage. The capacitor, which we know the capacitance is 10 microfarads, it has been charged to 15 volts, so we know there's a net charge Q naught. Q naught is not 15 volts because, well, the charge is in coulombs, not voltage. But we can figure that out without a problem. Capacitor brings in some energy. It is then connected to an inductor. We know the value of the inductor is 5 millihenries. We know the capacitor starts to discharge, charge starts flowing through the circuit, and the energy oscillates back and forth between the capacitor and the inductor. Now we're trying to find Q. So Q equals what? When our current equals 0.55 amps. There's two ways we can go about this. We do know the charge on the capacitor as a function of time is equal to Q naught cosine omega t. We know the current in the circuit is described by omega Q naught sine omega t. So one way to go about this is we know the current is 0.55 amps. We could find the time when the current has that value, and then take that time up here and plug it in the charge equation and find the charge. And I apologize for my very slow computer at the moment. Okay, perfectly valid way of solving the problem. For me, that would not be my first instinct, which doesn't mean anything, that's just me. My first instinct, though, is I know the total energy is constant. We're dealing with just an inductor and a capacitor, no resistor, and that is why I know the total energy is constant. I know the capacitor initially has energy, and I have the information to find that energy. I know the capacitance, I know the potential difference across the capacitor initially. That's given to me. Well, Since I'm asked to find the charge on the capacitor when the current is 0.55 amps, that means we're looking at a later moment in time when there's some energy on the capacitor. So 1/2 Q squared over C is the way I want to write the energy on the capacitor because I'm looking for Q. And there's some energy stored in the inductor at this moment in time because there's some current. Conservation of energy is my gut approach to this problem because I know energy has to stay constant in this circuit when there's no resistor, and I like energy. So in this circuit, we know the value of the capacitor. We know delta V that the capacitor starts with. We know C, we know L, we know I at this moment in time. Q is our only unknown. So first off, I see there's a 1/2 in every term. So I'm going to go ahead and cancel that. I'm also going to bring the inductor term to the left side because I know those values. And then I'm going to leave my Q squared over C on the right side for just a second. It's Q that I'm looking for. So Q will be the square root. I would have to multiply the C over. I'm going to write it this way for the moment, though I can factor that through. All right, so plugging numbers in, the capacitor's capacitance is 10 microfarads. And then I need capacitance again. Times the potential, the voltage the capacitor was charged to, and I need to square that, minus L is the inductor value, 5 millihenries, so I do need 10 to the negative 3 for milli. And then I is the current at this moment in time. That current needs to be squared. So the charge at the moment in time, the current is 0.55 squared. I just need to go ahead and put these values in. I'm getting 0.0001. That would be in coulombs. We could write it as 0.1 millicoulombs if we want. And technically there's a 0 after this there. Let's make sure this makes sense. Now, how much charge I don't really have a good concept on per se, but I can determine the initial charge the capacitor would have come in with and make sure my answer is not bigger than this maximum that came in with. So at least that can give me something to compare to. I know for a capacitor, the charge on the capacitor depends on the capacitance and the potential difference. So the capacitor's value, the capacitance, is 10 times 10 to the negative 6. And we know this was charged to 15 volts. So what, 150 times 10 to the negative 6? So this would be the most charge that would be on the plates of the capacitor. 150 times 10 to the negative 6. Let's get this to times 10 to the negative 3 so we can compare it to our answer and make sure our answer makes sense. If I move the decimal place 3 to the left, I would have 0.150 times 10 to the negative 3. So this tells me my capacitor comes in with 0.15 millicoulombs. So the fact that we got an answer of 0.1 millicoulombs, something less, is reasonable. We have some charge on the plates of the capacitor, but not all of the charge it came in with.